This car is so boring, but it might have the most underrated electric motor you ever heard of. Toyota put permanent magnet motor technology into a car before Tesla even existed. Then they wasted it on Prius, a car designed to maximize fuel efficiency with a spreadsheet. I'm going to pull that motor out and use it for something actually exciting. Can it be done? I have no idea. To turn Prius gearbox into standalone electric motor, I need to do 6 things. Install Open Inverter board, connect the power and get the motor moving in open loop mode, connect and test resolver before motor tuning, connect the throttle pedal and drive the motor. 6 steps, simple enough on paper. Alright, here we go. I have Generation 3 Toyota gearbox in front of me, an inverter looking innocent and Toyota reliable. 20 years of boring commutes, thousands of smug hybrid owners.
It's a hybrid. I just couldn't sit back and be a part of destroying the Earth anymore.
And now it's all mine. First order of business, I need to take control of this inverter. And by take control, I mean rip out the Toyota original processor board and replace it with an open source inverter. Basically, it's a brain transplant. Toyota spent millions engineering this thing, and I'm about to undo all that with a screwdriver and absolutely no plan B. Now, this inverter is sealed. Toyota used sealant between the top and bottom halves. I'm guessing probably to keep idiots like me out. Good news though, I already opened this particular unit before, so the sealant broken and it's just the screws now. Pop the cover off, swap the board, simple. What could possibly go wrong? Board in, time for the moment of truth. Quick power test to see if control signals are actually reaching the inverter. We are looking at PWM signal, pulse width modulation. Basically a square wave signal that tells the inverter what to do. Power up light, we've got an LED, always a good sign. When things light up, instead of releasing magic smoke, power rails check out, voltage is there. Now I'm connecting the forward signal to 12 volts and firing up the inverter in manual mode. This should enable the output signal. Should being the key word. And it's on. Here we go, the first small win. We are not dead yet, people. Toyota's secret starting to unravel. And this board didn't come out of thin air, of course. It was made by PCBWay. And I'm happy to say they are also sponsoring this video. It makes perfect sense, and this is one of the sponsorships where I genuinely use their services to manufacture this board. You upload your design files, and a couple of weeks later a professional PCB shows up at your door. And if you want to go one step further, they offer a turnkey solution. So they will source all the components from your bill of materials, place them and solder them onto the board. You basically send them the files and get back a fully assembled, ready to test board. No sourcing parts, no hand soldering, no cursing at tiny components at midnight. But PCBWay isn't just a PCB, they also do CNC machining and 3D printing. So if you're doing your own builds, PCB manufacture, 3D printing or CNC machining, please use link in the description below. Your first order will be discounted, but there is a danger you will be helping me doing even more silly things like this. And I will be doing more of them if you do. So, order things for you, but let's get back to the Prius now. Next up, I need to run the inverter with motor actually connected. For that, I need contactors. Basically fancy relays that handle the high voltage switching. Now, before you ask, no, you can't just slap 2 relays on the battery and call it a day. I wish. Here's the problem. The inverter has a massive capacitor inside, and a capacitor of that size, when it's completely empty, looks like a dead short to the battery. Smash contactor closed on that and the current spike will be so violent it can literally weld the contactor shut. So instead we do it the slow, the boring way. First we close the pre-charge contactor, which routes the current through a resistor. The resistor limits the current and let the capacitor charge up gradually and gently. Once the capacitor is fully charged, the voltage across the main contactor is nearly zero, so now it's safe to open the pre-charge and close the main contactor. No sparks, no welding, great. The inverter cover houses the capacitor and discharge resistor. Once that goes on, I'm blind. No measurement, no probing, no idea what's happening inside. And if something goes wrong, and let's be honest, something always does go wrong, I want to see it happening in real time. So naturally I want to remove the capacitor off the cover and mount it directly on top of the inverter. Coverless, exposed, absolutely not how Toyota intended it. To connect the contactors, I'm pulling out a wiring harness I built earlier when I first started messing around with this Prius gearbox. Yes, I have been down this rabbit hole before. No, I didn't learn my lesson. I won't be using every connection on this harness, mainly just the contactors, plus a start button and a forward switch. The Open Inverter board will handle contactor control automatically, switching from pre-charge to normal mode without me having to think about it. Now, the motor. The motor currently on the other side of the garage, of course it is, so before I can connect anything, I need to get it over here. This is the part where I attempt to wrestle what is essentially a very heavy, very awkward lump of metal onto a small trolley. I will let the footage speak for itself.
Yes, I'm winning! Idiot! Yes! Got it! Wow, this is wonderful.
Right, motor is mobile. Bringing it closer to the inverter, connecting the phase cables, and we're almost ready to see if this whole thing actually works. Capacitor mounted, wiring harness connected. Time for the moment I've been building towards, the first motor spin. I'm turning on the high voltage power supply. Don't panic, it's only 90 volts. Enough to ruin your day, but we're not exactly splitting atoms here. Then low voltage power supply goes on. At this point the main contactor stays open, but the pre-charge contactor closes, quietly doing its job, charging that capacitor up nice and slowly. Few seconds delay, deep breath, start button. Pre-charge sequence ends, inverter fires up and I can hear the contactor click. Beautiful sound. PWM signal appears on the scope. We are alive. Now I just need to punch a couple of parameters into Open Inverter web interface and this motor should spin. Values entered, here we go. And I hear a clunk. Just a clunk. Motor twitches like it wants to move, but then it just stops. And then nothing. So I did what any reasonable person does when faced with unexpected electrical problem. I pondered, I measured, I stared at it some more, and then it hit me. A light bulb moment. Literally, I've decided to use a light bulb. So instead of the pre-charge resistor, I wired a light bulb. Simple, elegant, slightly ridiculous. The bulb will glow when current flows and glow brighter as current increases. If pre-charge completes properly, the bulb should flash momentarily and go out. Visual confirmation. But here's a real genius of this. And I use word genius very loosely. By eliminating contactors entirely, I can instantly tell whether the problem lives in the motor, inverter or the supply voltage. Current will be limited by the bulb, but I have thought of that. I wired a manual switch in parallel with the bulb, so once pre-charge is complete and capacitor is happy, I can bypass the bulb entirely and confirm the full voltage is actually reaching the inverter. Simple, effective, why did I not start from that? Now I apply parameters and hopefully this time the motor will rotate and the motor comes alive. Increase current further and I get horrific, deeply concerning vibration. But that's not a clunk, that's energy, loads of it. But wait, what if the bigger motor just locked with the parking pole? For now, let's try MG1, the smaller motor. Toyota intended this one purely as a generator. Modest, sensible, very Toyota-like. Let's see what happens when we ask it to do something more interesting. Connected, parameters in, and we get vibration. Similar to what we had before, but it's actually moving in smaller steps, with continuous judder. What if I adjust the slip parameters? And now we try and flip spin 8. Oh, here it is. Smooth rotation, power, movement. Exactly what I was hoping to see 20 minutes ago. Small victory, but I will take it. Right, let's go back to MG2, the big one. swap the connections, dial in the smaller parameter slip, and it moves smoothly, no drama, no clank. Just a motor doing exactly what it's told. So we confirmed the motor spins, but spinning freely at constant speed is not exactly useful, is it? We do need precise torque on demand. To have that, we will need FOC, field-oriented control. Sounds a bit like a military operation, doesn't it? Imagine you're trying to push a merry-go-round. Timing is everything. If you push it exactly at the right moment and in the right direction, you add energy perfectly and it speeds up. But if you push it at the wrong moment or in the wrong direction, like it's coming back towards you, you just kill the momentum and waste all your effort. The electric motor works in a surprisingly similar way. To make the motor spin efficiently, you need to push on that spinning magnet at exactly the right moment. That's why we need a way of measuring exact position of the rotor. Good news on position sensing front. Prius gearbox already has such a device built in. It's called a resolver. Wire up the resolver using harness I already have. Rotate the motor by hand and I'm hoping that I will get angle changing from 0 to 360. Should be a quick job, right? No. Whatever I tried, I couldn't get the reading to reflect the true rotor position. Noisy, inconsistent, the readings were all over the place. I found 200 pages of extensive documentation on resolvers used by Toyota. Immediately got overwhelmed and decided to give up and move to MG2 resolver. Right, well, MG1 is dead to me now. I'm moving to MG2. This is like moving to bigger and better things. It's a bigger motor I wanted in the first place. Moved the wiring across to MG2 resolver connector, started the motor, pulled up the angle graph, 0 to 60 both directions first try. After that, I carried on with the tuning of the motor. This is mostly done with the use of black magic, as well as changing the sync-offs value to basically align our electric magnetic coils against the permanent magnets. Get it right and you're pushing the merry-go-round at exactly the right moment and in exactly the right direction. Get it wrong and you have a very angry motor that refuses to cooperate and a very confused engineer who has no idea why. There are no instructions for this specific motor, so there is no golden number written down anywhere. So I changed the value, tested it, changed it again, tested it again, repeated this process an amount of times I'd rather not disclose. I think I found it, the number, the specific value that keeps the magnets happy and the motor pulling in the right direction. I have written it down in a very safe place, called Open Inverter parameters set. I need to connect the pedal and test it now. Right, throttle pedal. Of course I'm using a Prius pedal for this one. And good news, I actually built a throttle cable adapter for this project a while back. Bad news, it's got Tesla connector on it. Of course I was using it with my Tesla motor, but this is a Prius motor, right? So these two things are not compatible and honestly I have no idea what I was thinking. The fix is simple enough though. Resolder 4 wires, swap the connector, done. After everything this project has thrown at me, 4 wires feels almost insulting. Throttle pedal connected, everything works first try, but I almost don't trust it. This is the moment of truth. Now I want to apply the gas. It does work. But let me tell you, it doesn't. After more experimentation, I think I broke something. I wasn't satisfied with the tuning and I went off and adjust sync-offs value further, and I think I pushed a little bit too far. The motor started spinning continuously and even once I released the throttle it still kept going. And this is where I made the decision that I knew probably a bad idea at the time, and now I can confirm was definitely a bad idea in hindsight. I changed the sync-offs value while the motor was still running. Loud clank, motor stops. And then the smell, that specific smell of burning plastic. Just hint of it, just enough to make your stomach drop. Everyone who works with electronics knows that's the smell you are dreading. Voltage on the inverter is reading 42 volts. Should be 90. I need to go back and test every power supply module individually and figure out exactly what I've managed to destroy this time. I must admit, this is the lowest point of the whole project. My power supply is made up of 4 modules, each producing around 30 volts. I went through and tested every single one of them. All 4 damaged, every last one. Oddly enough, that was the best news I had all day. If the power supply took the hit, there is a chance that inverter may not be damaged. I dug around and found 2 spare modules I hadn't used. I connected them up, did a quick test, motor spins. And now we put manual ID 5. Our motor is working. Good news, motor works. Inverter survived. I'm back in business. Bad news, I'm only down to 2 modules. 60 volts only. Not ideal. But staring at the power supply, feeling sorry for myself, I noticed something. Additional modules. Plus and minus 12 volts. 2 of them sitting there the entire time. That's extra 48 volts I've been ignoring for months. Necessity is apparently the mother of noticing things that were in front of you the entire time. Armed with a new configuration of the power supply, I've got back to FOC tuning. Except tiny little issue.
This actually won't work at all if the power supply cannot supply the current required to spin the motor as requested by the throttle pedal. Don't worry, there is a solution.
Am I supposed to know what that is? This is a lithium-ion battery. Of course, every time I pushed the motor harder, I could hear the power supply clicking, hitting its current limit, struggling to deliver what the motor needed. The root cause of my tuning problems from the very beginning: not enough current. The solution is a proper battery, which I don't have, of course. So I'm going to build one. I've got a pile of 18650 cells recovered from old laptop batteries. Those are leftovers from the days when I built my DIY BMS. Also, I already have PCBs with individual battery holders that let me charge each cell separately before assembling them into the modules. Incredibly tedious, absolutely the wrong way to spend the afternoon. But for the test battery it will do. I went through every single cell, checked capacity, pulled out anything that had self-discharged too much. The poor quality cells had given up the life entirely, so those went straight into the bin. I mean recycling center. These modules are designed to be connected in parallel. I'm going to connect them in series. Series connection gives me up to 90 volts across 3 modules, which is what I need. The configuration is 21S2P, which is 7 cells in series and 2 in parallel for each module. It's not a big battery, but it should have enough to run a few tests without immediately giving up. Battery connected. This is the moment of truth. Press the pedal, motor spins, smoothly accelerating exactly as it should. No clunk, no vibration, no burning smell this time. Hooray! I can't believe this is working. It was a current issue all along. The battery, however small that is, it gives us what we need. And this is the motor running. Very smooth control with the throttle pedal, acceleration. Toyota buried this thing in the Prius. I got it out, I blew up the power supply, but I made the motor spin in the end. Not bad.